Hi, everybody. We're still in chapter 11, which I think can best be described as an overview of endogenic processes, which certainly has to do with the dynamic planet, the fact that Earth is always changing, and um, and so that's why we started the chapter talking about endogenic processes and systems where the heat is coming from inside the Earth. And then we got into talking about the geologic systems, or the geologic cycle, and it being made up of subsystems. We talked about the rock cycle, and here we're starting with the tectonic cycle, and we're going to talk about plate tectonics. In this video, we're going to cover these first four bullet points. We'll talk a little bit about how plate tectonics came about. We'll talk about the importance of a process called seafloor spreading as it pertains to creating new crust. And then we'll also talk a bit about subduction and how that plays a part in the recycling or destruction of crust. And then we'll talk about, too, briefly, how these different processes lend itself to explain the formation and the breakup of Pangea, finally. Alfred Wegener wasn't around to see it, but with these new processes discovered, we could finally explain continental drift, or why Pangea, which we believe now really did very much exist. And we'll go over the evidence in this video of why we think Pangea did exist and has broken apart since it had formed. All right, the last three bullet points will be covered separately. So let's start in our tectonic cycle, talking about plate tectonics. The history, we'd be remiss if we didn't go back to some of the first mentions of continents being torn apart from each other. The fact that they looked like they fit together was really some of the first evidence that the continents had moved. Um, the language was a little more verbose, or loquacious, I suppose, um, at the time that it was written about. But here, Abram Ortelius in the late 1500s wrote that the Americas, North and South America, were torn away from Europe and Africa. That's on the other side of the Atlantic Ocean today, uh, by earthquakes and floods. And that's not actually technically wrong. There certainly would be earthquakes and some sort of seawater inundation while the continents separated, but it wasn't a catastrophic event, um, as many people used to think. Um, Today, we know that it's been happening very, very slowly. But this drawing, which reminds me of, I think, maps that I saw when I was in elementary school of South America fitting into that crook of Africa. And we can, we can still see that today on globes or other maps. It just looks like South America fits very nicely into that bend in Africa. So that idea has been around for a long, long time, but nobody explored it in a lot of depth until Alfred Wegener. In the early 1900s, he developed the concept of continental drift, and I wrote a whole big manuscript collecting data from lots of different sources and authors, and had the idea that all of the continents were once one single landmass, and he named it Pangea. That's where the name comes from, Alfred Wegener, um, in 1912. publishing that manuscript. His idea was that the continents floated on a mantle, solid mantle, something that's below the water. Thinking of it like icebergs floating around in the water or on the mantle that's below the ocean, and that's why it was called continental drift. That the continents just drift along. They drifted together to make Pangea, and then they drifted apart to where they are today. He had strong evidence that the continents had moved. It wasn't just that they seemed to fit together, although that was, as we said, a good line of evidence that had been around for a long, long time. But there was some other evidence, and I want to spend about a slide talking about each one of these. This isn't totally comprehensive, but it's some of the main points that he included in the manuscript that I'll just mention now. They're people didn't dispute the evidence that he used to uh, for the formation of Pangea to support that idea. But just a spoiler, he didn't have any way of explaining really how it would happen. But in any case, let's look at the evidence. We already looked at the fit of the continents, so let's just look at some of the fossil evidence that supports land masses being together at one point in time. This graphic, this figure here, shows four different species. I just want to focus really on the two of them, the Lystrosaurus over here, and Cynonathus, which is this little buddy over here. Neither of them can swim. As far as the fossil evidence tells us, they do not appear to be swimming organisms at all. So that means that they live only on land. One is a reptile and one is a mammal-like reptile, but still a reptile. That's a little beside the point. The point here is that Lystrosaurus and Cynonathus their fossils today are found on continents that are separated by large, large oceans. So between India, Antarctica, and Africa, we find fossils of Lystrosaurus. Between South America and Africa, we find fossils of Cynonathus. There is no way, given the present configuration of the continents, that we could, or that Cynonathus could have been in South America and Africa at the same time. There's no way. They can't walk there. And they're definitely not swimming across the Atlantic Ocean for Cynonathus, or for Lystrosaurus swimming across the Indian Ocean, or the the Indian Ocean, not swimming. And yet we do find their fossils across these continents. It only makes sense if these continents were all together and these reptiles could walk and or migrate. But the key is that they'd have to walk. And so there'd have to be land without any big oceans. There'd have to be some kind of land bridges between these areas. The same thing really goes for the Mesosaurus and Glossopteris. There's just slightly different reasons why these land masses have to be connected. For Mesosaurus, it's that it only swims in fresh water, so it's not getting into any oceans. Glossopteris is a plant that just has heavy seeds that could not be transported across the ocean that separates Australia and Antarctica. So again, for different reasons, these fossils support at least these five continents being joined together. We have what's called paleoclimate evidence. This is climate data, evidence of different types of climates in the past. That's where paleo comes in. That's past climate evidence. And so, looking at different types of climates, there's seven that are listed here and seven that are shown in the diagram here. Um, the ancient climate data suggests to us that these continents were also together. So we were just looking at South America, Africa, India, Australia, and Antarctica. With the fossil data supporting the idea that these five continents had been joined together, well, it turns out looking at glacier climates, past ancient glacier climates, also supports that idea. So it's not just the fossils. We find evidence of glaciation in these areas of all five continents. Um, and very different in some cases from today, not Antarctica so much, but anyone familiar with the climate of India today, uh, any part of India we would not call glaciated. It's not cold enough for glaciers. It's the opposite. India is very, very hot. It's the tropical, subtropical climates. Very, very hot. Australia, the same thing. A lot of Australia is desert today and very hot most of the year. Um, but we do have evidence of glaciers being in these locations at a point in the past. In the same way, we have evidence of deserts crossing Northern America, Canada, into Europe. There are no deserts in the in that part of North America or Europe today. Similarly, with some of the tropical climates, there's kind of like proto Mexico right in there. Um, no, we don't consider Mexico to be tropical. It's mostly desert. So again, these sorts of climates, first of all, they match up when we arrange the continents in certain ways. Um, and yeah, that's the important part. They do match up when we align the continents in certain ways. So paleoclimate evidence is another thing that is backing up this joining of continents, as we'd see in Pangea. Uh, those are the main lines of evidence that we'll talk about here, just for the sake of time. Um, and as I said, those lines of evidence from other scientists who collected them, it was solid, it was accepted. It's like, yeah, we see that. We understand that all makes sense. But from the time that Alfred Wegener proposed it, 1912, into the 20s, into the 50s even, which is past the time that Alfred Wegener was alive, continental drift was still very controversial because, as I said before, he could not explain how the continents move. Scientists always came back and said, what monumental forces would drive these massive continents to be moving? Just kind of drifting across the oceans, coming together and apart. Like, what could possibly do that? So, that theory of continental drift was not accepted. The whole idea, in fact, was not accepted until the 1960s. The studies technically started in the 50s, but it was really in the 1960s that new information started to come together. And that was led by Harry Hess and Robert Dietz. They were in the Navy, and they were geophysicists. The the U.S. military in general does employ scientists, and in the Navy, geophysicists are employed to study the ocean. As they go through the ocean, they use remote sensing. They use seismic data. They use sonar while they're in the ocean. So Hess and Dietz were in submarines and on naval ships using sonar. Um, and let me skip forward a sec. Okay. And came up with hypotheses from working with other geoscientists with this idea, from Alfred Wegener from, decades beforehand. Um, but the important part here is that using sonar um, was a big, big thing in the early 40s, 30s and 40s. And if anyone can guess why were these Navy uh, folks using so much sonar in the ocean? I mean, their primary objective was in World War II looking for enemy subs, U-boats, German subs. So they constantly had the sonar running for that purpose. But while the sonar is running, finding U-boats or not, the sonar was collecting essentially ocean survey data. That was finding the bottom of the ocean floor and telling us how deep the ocean was. And just, yeah, constantly running while these ships crisscrossed the whole Atlantic Ocean over years and years and years. And so we ended up collecting these ocean floor maps that we had never had before. In Alfred Wegener's time, we did not know what was at the bottom of the ocean, like in the middle of the ocean. We didn't have the technology. We didn't have, I mean, maybe we had sonar, but we didn't have the swath of data that was collected during World War II because we had so many ships and subs all running sonar. So in any case, we ended up developing this huge bathymetric map from sonar. And then we also discovered something else that we hadn't known much about, or again, didn't have the massive amount of data that we have today, which is about, um, I'm just going to say magnetic field information on the seafloor, the rocks that make up the seafloor. And both of these combined, I'll explain this a little in just a sec, but both of these combined led Hess and Dietz to develop the process or the concept of seafloor spreading. And seafloor spreading is the mechanism that was missing from Alfred Wegener's theory of continental drift. Subduction kind of goes hand in hand with that now, but seafloor spreading was a major, major development. Um, Incredibly so. And kind of fast-tracked continental drift. They abandoned that term because the continents we determined were not just drifting, but we're doing something else. So we came up with the new name of plate tectonics, the theory of plate tectonics. And so let's get into that a little bit more. The oceans themselves, if we drained all the water out from the oceans, this is what the bottom of the ocean floor might look like. This is the Atlantic Ocean, just kind of as an artist has drawn it. South America is here to the left, and Africa is here to the right. No water in the Atlantic Ocean. And so we see the bottom of the ocean floor and all of the relief that is here as well. There's lots of little volcanic islands. Some of them reach go above water to make them true islands, but some of them don't go above water, but they're still there as little like dots and little mountains that come up from the seafloor. They just don't come above water. So there's lots of that going on. Um, we in the middle of the Atlantic Ocean, which again is where a lot of those ships and U-boats were traversing, right, between Germany and the US and of course all around Europe. Um, the ships going back and forth discovered a ridge, a high point, I'll say a linear high point from Iceland and north, but also south of Iceland and coming right in between North America and Europe and coming right in between South America and Africa. It's a high spot. It's what we call a ridge, a long linear ridge in the middle of the Atlantic Ocean. And we also discovered a little later on that these ridges are volcanic. So these are essentially big fissures or mountains because they are high spots. It's a ridge, but they're volcanic in nature. And, after some additional study, we decided that, for one thing, we're going to call them mid-ocean ridges or MORs because they're in the middle of the Atlantic Ocean. So, mid-ocean ridges. And that it marks the edge of two plates. So the boundary between two plates, like puzzle pieces, I could trace out the line between the two puzzle pieces. On the left in this figure, I have North America, the North American plate, even that Greenland is a part of, and half of Iceland is a part of. That's the North American plate. And on the other side is the Eurasian plate and the African plate down a little further south. And this line of volcanoes, the ridge, the volcanic ridge, that marks the boundary between the two. We also discovered that the two plates, or the four plates, if we want to include Africa and South America down here, they are moving away from each other. So North America is moving to the west, and Eurasia and Africa are moving to the east. This is the spreading that comes into play when we're talking about seafloor spreading. Going back to the figure on the left, again, we have the ridge right here in the middle, the North Atlantic plate moving to the left, the African plate moving to the right, and the ridge itself, it's erupting. It's erupting lava, which means there's magma underneath it, and that magma rises um, and helps to push the plates apart. They're spreading apart from each other. They're being pushed by the magma that's rising. The idea, though, is that helps. That helps the plates move apart from each other. That it's being pushed by new magma coming up to the surface. And so this video, I really like this video. It shows some of the lava that's erupting at these mid-ocean ridges and what that lava looks like. Yeah, sorry, I do not endorse these ads. Okay, right here. Yeah, so this whole video is happening underwater at a mid-ocean ridge and illustrates um, how magma is erupted at the surface and how it ends up creating new oceanic crust. Um, when that lava cools off, it okay. Before I start this, it yeah, as he said, it's constantly erupting, maybe not in one spot forever and ever, but all along that mid-ocean ridge. There are very consistent eruptions happening. And so we are constantly creating new rock that just by volume is pushing the old rock away. Just another short video about what the pillow lava, he mentioned a pillow lava. This is a good representation of what a pillow lava looks like. It's lava. It just erupts as this kind of bulbous shape, which is different than lavas as they flow across land. Um, I won't say that they really look like pillows, but you know, geoscientists are creative. I don't know, how do I do this? Right. So that's a pillow lava, and it just sort of keeps expanding and moving. Kind of want to say almost like a, I don't know, like a worm or a snake. It just kind of keeps taking the sinuous path, going downhill for the most part. The middle of it is still very hot as liquid lava. But the see if I can go back a little or all the way back. But the outside of it is cooling very fast because lava being in contact with very cold ocean water is going to freeze, cool, crystallize really fast. Um, it's also boiling some of the seawater, which is some of the bubbles that we see. It's releasing some gases, which is also some of the bubbles and what looks like steam. But yeah, this is from the bottom of the ocean, and what it looks like at mid-ocean ridges. That's the lava that's erupting at mid-ocean ridges. So, the the bathymetry at the bottom of the ocean aside, which is the relief, the ups and the downs of the bottom of the ocean, it's called bathymetry. That aside, we also had magnetic field data um, also confirm the idea that these two plates are being pushed apart and at a fairly constant rate during various time periods. What we have to go back and remember is with our magnetic fields over Earth's history, they have flipped, right? Our magnetic fields have flipped from north at north to north at south. And it's done that hundreds and thousands of times. That's from the last video or two videos ago. Um, we see certain types of rocks locking in that reversal information or the magnetic field information. Certain types of rocks, luckily, the types of rocks that form at the bottom of the ocean, these are basalts and gabbros, um, mafic rocks. Those types of rocks lock in the magnetic field orientation. It tells us that those rocks can tell us if we use the right instruments, those rocks can tell us whether north was at north or north was at south when the rocks formed. And so the rocks forming here at the center of the mid-ocean ridges, new rocks are forming here. Well, when they cool off completely, they're going to lock in that magnetic field information. They have, like magnetic minerals in them that will align themselves with the magnetic field. That's a simple way of putting it. So these different colors here I know it's grainy, but it was the best I had at the time. The different colors here represent green being maybe north at north, and orange being north at south, green north at north, orange north at south. And so we have evidence of magnetic field reversals and also the pattern of those reversals. The new rock that's forming here, I'm actually going to go to the figure on the left here to describe this. The new ocean floor that's being made at time A, that rock is all forming while, let's say, north is at north. That's a normal polarity at that time. And we're just going to color it yellow for visual purposes. Um, all of that rock is forming, the plates are spreading apart continuously, but this rock is all forming while the polarity is normal, north at north. But at some point, let's say, after a couple million years, the magnetic field's going to reverse itself. Again, not boom overnight, but geologically speaking, pretty quickly. So now at this point, time B, the magma still erupting, the lava still forming, creating new ocean crust, moving the plates apart. Now the polarity is reversed. And so we form some new ocean crust with the reversed polarity. Well, the plates continue to split. And so that is why we see some yellow on one side, some yellow on the other side. It is split. This big yellow field, it split it into two parts because the crust continues to pull apart. So the reverse polarity here being erupted, well, boom, times C. Now we have back to normal polarity. And so we have yellow again. But the red has been split because, again, it's just been pulled apart in that way. Um, and that's the idea behind the animated GIF here. Seeing these colors kind of forming all together, but being split apart at the same time as the crust and as the plates move away from each other. So there's a big green spot, but it's being split when the orange forms. And back and forth and back and forth. Okay, so this is where magnetic field polarity and its reversals help back up this idea that the seafloor is being, well, newly created at the ridge, but also that it is pushing the plates apart. And the idea here too, that was critical for, yeah, that was critical for seafloor spreading. The idea that the ocean floor is connected to the continents. I haven't mentioned that yet, but that is critical for the plate tectonic theory, that ocean floor is connected to the continents and that it's all of this, the ocean floor and the continents on the North American plate, it's all being moved in one direction. Same here for Eurasia and the oceanic lithosphere connected to it. That is all being pushed to the right, to the east. So that is where the magnetic field and pole reversals helped us kind of solidify plate tectonics as a theory. So I have one question for us right here as a review question. Again, as usual, if you want to pause and think about the question, go ahead and do that now. I'll give you a second to do that while I read the question. Continental crust is composed of A, granite and is less dense than oceanic crust. B, basalt and is less dense than oceanic crust. C, granite and is more dense than oceanic crust. Or D, basalt and is more dense than oceanic crust. So I'll just give you another second to pause if you want. And the answer is A. Continental crust is composed of granite and it is less dense than oceanic crust. If we went back to the previous videos earlier in the chapter, we'll see that. It'll say continental crust is mainly made up of granite, and all continental crust is less dense than any of the oceanic crust. And just to reiterate, if I haven't said it before, oceanic crust um, oceanic crust is more dense than continental crust, and that's why oceanic crust will subduct, and why continental crust will never subduct. Just to back that up here, and kind of look at this plate tectonic theory overall, we have been talking about the lithosphere, right? Because remember, the lithosphere is what makes up a tectonic plate. The lithosphere is rigid. It's made up of the crust and the upper mantle, layers that are cool enough to be rigid and to move as one coherent piece. Uh, and and so plate tectonics describes a theory where the entire lithosphere is moving, and the asthenosphere below it might be helping the movement of the lithosphere, like these arrows sort of suggest here. But the asthenosphere itself is ductile, it can flow. It's solid for the most part, despite it being colored in reds and yellows. Um, that's what we think of magma, right? But most of the asthenosphere, it, by most, I mean like 99% of it is solid. Magma only occurs in certain places. And if you want to know more about that again, physical geology is a good place to, uh, is a course that covers that in more detail. But in any case, I just wanted to illustrate the fact that the lithosphere, or in this case, the South American plate, we have continuous lithosphere from the ocean into the continent. That's all one plate, it's all connected. It is technically two different compositions because they're made in two different ways, but it's all connected. So the spreading ridge here with the magma rising at the ridge, it is pushing the entire plate to the right, to the left in this case, or the African plate over here on the other side of the ridge, right? Where the two are touching, that's the boundary. But it does mark the edge of both the South American plate and the African plate. And so while the South American plate is being pushed to the left, the African plate is being pushed to the right. Again, with both oceanic lithosphere and continental lithosphere or continental crust in this case. I also like this diagram because one, it shows that the continents aren't just disconnected and drifting around like icebergs, but we see the spreading ridges. We see the seafloor spreading happening here, pushing the plates in opposite directions. But we also see the subduction zones. On the other side of South America, we have another oceanic uh, lithosphere, This happens to be the Pacific plate, the Pacific Ocean, the Pacific plate. And the Pacific plate here is converging with the South American plate. They are moving towards each other as these blue arrows indicate. And because the ocean lithosphere here is denser, oceanic lithosphere is always denser, it will sink beneath the continental lithosphere of South America, where they are colliding. And so we are creating new crust, oceanic crust, at the mid-ocean ridge or the spreading center. We're creating new ocean crust as the magma and the lava rises and solidifies. That's new rock. But here in the subduction zone, the oceanic lithosphere is boom, sinking into the mantle and being recycled. But it is destroying that oceanic lithosphere at the convergent boundary. We do have a whole lot of plates, tectonic plates, that are both oceanic and continental lithosphere, but some aren't. The Pacific plate is almost entirely oceanic, um, is entirely oceanic lithosphere. Um, but most are mixed. And so I just wanted to emphasize that uh, on this slide. And again, how the seafloor spreading provided that mechanism for the continents moving. It's not just the continents floating around in the oceans. The continents are connected to the bottom of the ocean, to the oceanic lithosphere, and the whole thing is moving. That's a big difference between continental drift and the theory of plate tectonics, and it's the reason why the theory of plate tectonics has been accepted for decades. This is a pretty nice uh, depiction of the of Pangea, and so I'm just going to play this maybe a couple times. Um, this isn't the entire breakup of Pangea, but it represents some of the important parts, and we end up looking at the continents being how they look today. Um, the reason that things look a little odd as they're moving is because this animation also includes sea level rise and fall. Technology is shining the light on today's consumer. Stupid ass. Um, so just before I play this again, I'll just mention that we are looking at Pangea already partially separated. We can barely see North America over here. It's already kind of moving off the map. But Europe is here. It's under a lot of water. Africa has this large intercontinental sea running through it. There's South America. Um, South America and Africa will continue to separate, but sea level is also going to be going down as we watch the continents continue to move. So that's why we'll see the intercontinental sea across the Saharan desert disappear because sea level is dropping at the same time as the continents are drifting apart. All right, so yeah, North America, but here's the real split of South America and Africa. Sea level is dropping, dropping, dropping. And the oceans, the Atlantic Ocean here is continuing to spread further and further and further apart. Because again, we just keep adding new oceanic crust. It keeps pushing the plates apart. And that's where we'll stop for the video. Uh, the last video, or the last part of the chapter, is going to be um about the kind of organization of the plates and how they move, and the landforms that they end up creating because of their movement. That's the last part of the chapter that we'll have after this.